Good afternoon. So today we study section 5.3, the fundamental theorem of calculus. First, I would like to motivate this topic by mentioning two things that we have learned so far. So we defined a definite integral of a function f to be equal to the limit of a Riemann sum. Okay, on one hand. On the other hand, from calculus 2a, you know all about functions, their derivatives and antiderivatives. So if f prime, sorry. So let's just write it f of x, okay? These are seemingly unrelated concepts because here we have the Riemann sum, we have the partition, we have all that, and here we have calculus as defined before, but there is a close connection between the two. And this connection is explained in this theory that we are going to look at today. So it will become clear as we go on. To start with, I'm going to define a function g of x that's equal to an integral from a to x of another function f. So f is a given function, and we integrate like this, okay, between the limits a and x. This is slightly unusual because the argument of the function on the left coincides with the upper limit of integration on the right. So what does this mean? Let's draw an example of a function f. Okay, identify the initial point A, and assume that this function is defined between some points A and B. And I want you to think about this shape as a carpet. This carpet is kind of long, and it has this shape, and it was cut this way. Now I want to buy a piece of this carpet, and I define where I want them to cut it. So for instance, I can cut it here, at this point x. Now the area of my carpet is everything here. If I tell them to cut it here, then the area of the carpet I buy is this. So this area is exactly defined by the function g. I go from a, and I stop at x, and x is my variable. I go as far as x. Okay? So as an example, we'll calculate such a function, okay, or tabulate such a function. I give you an example of f, but that makes it simple to draw g. So let f have the following shape. Goes like this. It's a piecewise linear function. Like this, okay? This is t, this is f of t. And given the function f, we're going to draw the function g. Again, the definition is given here. And instead of a, I can write 0, okay? It starts at 0. F of t dt. So first, let's figure out g of 0. What's g of 0?
0.
Is 0. I integrate from 0 to 0. Obviously, this is 0. So I can write it here. Like this. Now g of 1. How do I calculate that? I start at 0, and I cut it here, and evaluate this area, right? What's it equal to? Because my function is so simple, I can just figure it out from the geometry of it. The base is 1, the height is 2, and it's a right triangle. So this is equal to 1 times 2 over 2 is 1. So I could put here the first value of 1. Questions? Very good. So g of 2. Instead of stopping here, I'm going to stop further. So it's this whole area. And I'm not going to calculate this again, because I already know this is equal to 1. I have to add this other piece. It has area of 1 times 2. So it's 1 plus 1 times 2. The rectangle is 3, which gives me the value 3. I can also start drawing g of x. I already know the values at 0, at 1, and at 2 is 3. G of 3. I have to integrate some more, so I add this other triangle. It's the same as the first one. The area of this triangle is 1/2. Is 1, because the height is 2. This is 1. So this is 3 plus 1 is 4. Now there is something more interesting. G of 4. What do I have to do here? My example with the carpet doesn't really work because I have negative values here. This is more general example. I have to integrate from 0 to 4, so I have to include this area. But of course, this comes with a negative sign, right? So I take this and subtract this area. So I have 4 minus 1 is 3. Finally, the last point we are going to try is g of 5. So I go further. Can you tell me whether g of 5 is greater or smaller than g of 4? Smaller, because I subtract. Okay, the difference is a negative quantity. So this is given by 3 minus 1 is 2. So I tabulated this function at a few points. The actual graph is harder to draw because I don't know the points in between, but it's something like this. Okay, this gives you a general procedure of how to think about such a function. And now I want to show you why we define this function. Okay, this function appears in the definition of the fundamental theorem of calculus. So fundamental theorem of calculus, part 1. The statement is that if f is continuous on AB, then this function g is also continuous, and the derivative of g with respect to x is given by f of x. Okay, so this is the main statement of the theorem, and you can see that g is the integral a definite integral of f, and f is a derivative of g. So already you see some connection between the definite integral and differentiation. So we can say that here in bracket that g is an antiderivative of f. So this statement can be proven rigorously. Instead of proving it to you, I'm going to give you a motivation, okay, a picture example somehow of how you can think about this theorem. So here is some graph of f from A. This is x. And again, in this example, let's think of f as positive, and think of g as the area of the carpet. And you tell me where to cut it, okay? You tell me where to cut. So you define x as a customer. I cut it, and you calculate the area. That's your function g. So now I want to evaluate this statement. What does it mean? On the left, it involves a derivative of g. So let's remember the definition of a derivative. This is the limit as h goes to 0 of g x plus h minus g of x over h, right? So I want to evaluate approximately this derivative by first looking at this object, g of x plus h, then at this object, and then looking at their difference. So consider g of x plus h minus g of x. So let's start with g of x. That's the area up to here. To calculate it by using our definition, we have to split it into a bunch of very thin stripes, make them into rectangles, calculate the area of each, add them up. So, and that's how you calculate the area of that piece of carpet. Okay. So this is g of x. Now, what's g of x plus h? Let me take a different color. To calculate g of x plus h, I don't stop here, but I stop at x plus h here. So it's going to be the area all the way up to here. This expression here is the difference between the two. What's it equal to? The difference is given by this stripe. So this is g of x plus h minus g of x, right? Each g is the area. G of x plus h is slightly bigger, and the difference is this stripe. So I can write here, approximately. I already calculated a lot of stripes in this class. We have to take the base multiplied by the height. The base is h, because that's the difference here. So it's h. And the height, for instance, if we use the left-hand rule, that's the value of f at x. So f of x. Now I'm going to divide both sides by h. So I have g of x plus h minus g of x over h is equal to f of x. And this is approximately g prime of x. That's the expression that appears in the definition of the derivative. If we take h very small, this is approximately it, right? Or we can take the limit. So I get this is this, okay? So this is not a proof. Please consult the textbook for the rigorous proof. This is just an explanation of how this might work. Okay, now practical examples of this involve some very important problems. So let's start with the following. Define g as an integral, say from 0 to x, tangent squared t dt. Okay, calculate g prime of x. So this is done simply by applying this theorem. The fundamental theory of calculus part 1 states that this derivative is simply the integrand that appears in the definition of g evaluated at x. So we simply take the integrand tangent squared and evaluate it at x. And that's it. That's the answer. So the derivative of this rather complicated function can be calculated very easily. And note that we don't have to ever differentiate the integrand. It could be a rather messy, complicated function. We'd never have to differentiate it because of that theorem. It tells me that I'm taking the integrand and evaluate it at x. And that's my answer. Questions? Okay. Let's do another example. Suppose that g of x is given by an integral from 5 to sine x log of 1 plus t squared dt. And we need to calculate g prime of x. Okay. So with this example, if the top argument here, if the top limit was simply equal to x, what would we do? We would take the log and we would write down log of 1 plus x squared, and that would be the answer, because that's what the theorem tells us. Here it's a little bit more complicated, because instead of x, we have sine x here. So what we need to do is we need to introduce an intermediate variable. So change of variables. We define u to be the upper limit here. And the function g of u is now given by the integral from 5 to u. And now I can apply the chain rule to calculate the derivative of g with respect to x. dg dx is now dg du times du dx. You recognize this as the chain rule. By the way, now is a good time to review chain rule. You have to recall what it is. Okay. It's a way to evaluate a derivative indirectly. When g is a function of u and u is a function of x, we can differentiate g with respect to x, but we have to do it through differentiating it with respect to u. So first we go dg du and then du dx. Remember this? Yes. Chain rule. Okay. So why do I have to do it in such a complicated way? Because I want this problem to resemble the fundamental theorem of calculus part 1. My function wants to have its argument here. So I assigned u to be sine x, and now my argument appears in its pure form as a top limit of the integral. Now, this definition allows me to calculate this object, dg du. So let's do everything step by step. So what's dg du? I have to take this function and differentiate it with respect to u. So this is fundamental theorem of calculus part 1. We simply take the integrand and evaluate it at u. That's the answer here. dg du. And of course, eventually we want everything to be expressed in terms of x. So I write it by remembering that u is sine x. Okay. So that's this first component. The second one is du dx. This is really easy. I just defined u to be sine x. So from here, I can just say that it's cos x. Therefore, altogether, the answer is log of 1 plus sine squared x times cos x. Questions? Okay, I'll give you another example, which is slightly different. Let's define g as an integral from x to 20 of square root of t4 plus 2 dt. What is g prime of x? Again, it's a variation on the topic, on the theme. We have something like this. But unfortunately, the argument x appears as the bottom limit, not as the top limit. So what should I do? Exactly. I flip it. So all I have to do here is to write it as an integral from 20 to x. But there is a small price to pay. What's the price? Exactly. But it's not a big deal. So now in this form, you can see that this is just like here. And I can evaluate the derivative, remembering to include the minus sign. So it's minus, and then I put t to the 4 plus 2. I'm sorry, x 4 plus 2. That's all. So again, very important. This theorem tells me that I do not have to differentiate the integrand. I just write it down as it is, evaluating it at my variable. Question? Say again? Why did we flip it? Because I want to use this theorem. And in the theorem, in the definition, x appears on top. So it only works for this definition. It does not work for this definition. But once I flip it, I can do it. More questions? Okay. Another one. Let's define G to be something like this. This is the hardest example of all. Okay. I'm running out of functions here. So for instance, T8 sine T. I don't know. Okay. So now we have everything. We have the argument x both at the top and at the bottom. And it's not quite x, it's a function of x. So we have to do a few things. First of all, I want to bring this to the form where I only have x either at the top or at the bottom. To do this, I remember that if my integral goes from a to b, I can insert a point c and go from a to c plus from c to b. Okay? So that's what I'm going to do here. I'm going to insert an arbitrary constant, c, like this. Okay? I split my integral into two. Between the lower limit of integration and the upper limit of integration, I inserted a constant, and I don't really care what the constant is because my answer will not depend on it. Okay? but with any constant, it'll work, right? Just like here. This is one of those rules of integration that we looked at. And now the first integral contains x only as the lower limit, and the second one only contains it as the upper limit. So it's a little bit better. Now, the hard bit, again, is that it's not x, but a function of x. So I have to come up with some intermediate functions. So let me define u to be cosine x, and v will be x cubed. So I can really do them separately. g1 of x, or g1 of u, rather, is going to be an integral from u to c and g2 of v goes from c to v of the same function. And since this is a sum, I can differentiate them separately. So dg1 dx is dg1 du du dx. Chain rule applied to the first of these functions. The first component comes from the fundamental theorem of calculus part 1. Again, we take the integrand and evaluate it at u, remembering that we have to flip it first, so we get a minus sign. So a minus u to the 8 sine u. Okay, so this is dg1 du. And now du dx. From definition of u, I have minus sine x. Okay. The second one, dg2 dx, is dg2 du, dv. It's a function of v times dv dx. I'm dealing with this function. So again, it's v to the 8 sine v. What's dv dx? I have to look here. My definition is v is x cubed. So it's 3x squared. So this is dv dx. I have to put everything together. So g prime of x is the sum of these two terms. And I have to, the last thing I have to do, I have to substitute the definitions of u and v in the final answer, because I want everything to depend on x. So I have minus cosine 8x sine of cosine x times minus sine x plus x cubed to the 8 sine x cubed times 3x squared. Okay. So this here is v. This here is u. Questions? Question? So I have to, here I have dv dx. Yeah. dv dx. My v is defined as x cubed. So its derivative is 3x squared. Okay. Over here I can also write du dx is negative sine x. So that's these two objects, du dx and dv dx. They come from the chain rule. More questions? Okay. So now let's move on. And we'll talk about the fundamental theorem of calculus part 2. So the statement of the theorem is probably familiar to you. If f is continuous on the interval a, b, then we have a way to calculate a definite integral of f. It's given by f of b minus f of a, where f is any antiderivative of f. Okay. So the fundamental theorem of calculus is probably one of the biggest results in all of mathematics. Why? Because this gives us a very simple way to calculate integrals. Once we know this rule, we never have to evaluate Riemann sums and take the limits. We can all we need to do is to figure out the antiderivative of the integrand and evaluate it at the two limits of integration. Yes, this is good news. And but I want you to appreciate the depth of this result. On the left, we have that thing with strips, the rectangles, the limits. On the right, we have the antiderivative. How is it that they meet in the same formula? And this is what I'm going to prove to you. This is the actual proof, but it's very easy. Okay? I'm going to use the first part of this theorem to prove this. And the key is here. We have the antiderivative. So let's recall that if we define that funny function g, okay, to go from a to x, f of t dt, then according to the fundamental theorem of calculus, part 1, g prime of x is f. Okay, we said it a few times, but what it means is that g is an antiderivative of f. But you know how it is with antiderivatives. There's infinitely many of them. But if you know one, you know them all, because they only differ by a constant. So any other antiderivative of f is given by g of x plus, let me write that, sorry, is given by g of x plus c. It can only differ from this one by a constant. So fundamental theorem of calculus, part 1, identified one of the antiderivative of f. It's given by this funny function. Okay, and now we know the most general antiderivative. It differs from it by a constant. So this is a general statement. Any antiderivative is given by this. And now I'm going to prove this theorem by starting on the right and going to the left. So on the right, we have an antiderivative evaluated at b minus the antiderivative evaluated at a. So I'm going to use this expression, which involves g, and I substitute it here. And you will see that eventually I will show you that it's equal to this. And it's very simple. So let's write it down. F of b minus f of a. What do I have to do? I take this expression, and first I insert b instead of x. So I get g of b plus c. So this is f of b. Right? This first term is given by this evaluated at b. Minus, now I have to evaluate f of a. I go here again, I do the same thing. It's g of a plus c. Okay. So now tell me, what is g of a? What's it equal to? Go to the definition. Go here. It's 0. I can integrate from a to a. So g of a is 0. I write it down here. From a to a f of t dt is obviously 0. So that simplifies my life, because this is 0. And I can rewrite it as g of b plus c minus c. What's g of b again? I go here. This is my definition. It's an integral from a to b f of t dt. So I started here, f of b minus f of a, and then end up here. Okay. So it's not a mnemonic rule anymore. We can prove it. We can prove this amazing result by looking at this intermediate function g. Okay. And this result relates a definite integral, which has the meaning of area often, and the notion of antiderivatives. Questions? Okay, so let's practice. So a large part of this course will be devoted to evaluating integrals with the help of the fundamental theorem of calculus part 2. So the task now is reduced to figure out the antiderivative. But we start simple. We start from something very easy. The first example is something that we have to do, okay? Oh, what am I writing? This one. This is our favorite. I already asked you 5 times last time. I'm asking you the 6th time. What's the answer here? 1/3, right? We calculated it by we're going through the great pains of deriving the Riemann sum and taking the limits. So it better be equal to the same thing when we use our new result. So we have to, what do we have to do? We have to evaluate the antiderivative of x squared. It's equal to x cubed over 3. Okay, so we have to take this, evaluate it at 1, minus f of 0. Now, notation. In this class, we'll use a convenient notation, f of x, then I put a square bracket from a to b, or from 0 to 1. Okay, which means that I take this function at the upper limit minus the same function at the lower limit. So I can write x cubed over 3 from 0 to 1. So that's 1/3 minus 0. Thankfully, it's the same answer. Okay, so that completes the circle. Questions? Okay, let's. The next example is also quite easy. We'll look at the integral from -1 to 2 e to the x dx. That's a good function because we can very easily remember the antiderivative, right? So f of x is just e to the x. Like this. So we have to e to the 2 minus e to the -1. Do I have to put plus c here? No. Why? Because we have to think of the object on the left as a number. If the function is positive, it's the area. And the area is not defined up to an arbitrary constant. It's just defined as a number. Okay? If the function is non-positive, then it's a net area. But nonetheless, it's a number. So we should never be confused with the notation. It looks like an antiderivative, but it's really an integral, a definite integral. And the answer should be a constant. Okay? And one more example. is like this. So calculate the integral between 0 and b sine x dx. Okay, so the antiderivative is negative cosine, right? So we have negative cos x from 0 to b. Okay, minus cosine b. Then I have minus with a negative, so plus cosine of 0. Now we have to remember what cosine of 0 is. So I have 1 minus cos b. So evaluate at b equals 2 pi. Okay, so the integral from 0 to 2 pi sine x dx is equal to 1 minus cos 2 pi. What's the cosine of 2 pi? It's also 1, right? It's a periodic function. So the answer is 0. Should I be surprised or not? Could I have predicted this? Yes. So we can look at it graphically. We are integrating sine, okay, between 0 and first we did it up to some arbitrary limit b, so that would be, it doesn't have to be 0. But when we take b to be 2 pi, we can see that this integral is a signed area defined by this minus this. And because the two areas are the same, we have a1 minus a2 is 0, and the answer is 0. Questions? Okay, so this illustrates the fact that it's often very important to look at the graph of the integrand and kind of figure out what the answer should be. Okay, and this is very well illustrated by the last example for today, which is my favorite. So let's calculate the integral from -1 to 3, 1 over x squared dx. So what I'm going to do next is wrong. Okay, I just tell you that this is going to be wrong, and don't do this at home. So I'm going to blindly follow the instructions of the fundamental theorem of calculus part 2 without thinking much. So I'm going to say, okay, what's f of x is x to the -2. So the antiderivative is x minus 1 over minus 1. So it's -1 over x. I'm going to put that down here and go from -1 to 3. Okay. Now the rest is easy. So I have -1/3. When I evaluate the bottom limit, we have to count how many minus signs we get. So we have minus from here, we have a minus from here, and another minus because we go minus this limit, right? So altogether it's a -1. So it's -4/3. Now, I can tell you that this is completely wrong, and it should be obvious that it's completely wrong. Why is it obvious? Because we should draw the integrand. Okay, let's draw the integrand. The integrand is 1 over x squared. And you can see that this is an even function of x, and it's always positive. So it kind of goes like this and like this, the same on both sides. I'm sorry, my picture is not the same, but so it goes from -1 1, 2, 3. So you can see from the picture or from the formula that the function is positive. Now I integrate it, and I get a negative number. So now you can see that it's completely wrong, right? We don't know yet what the mistake is, but it's completely wrong. We cannot have a negative integral of a positive function. Okay? So now we have to think what is wrong. The wrong part is also obvious from this picture. The fundamental theorem of calculus, part 2, which I unfortunately erased, stated that the function has to be continuous. And here we have a singularity. It is continuity that we cannot get rid of. So in fact, so we have to cross this out. We cannot just blindly apply the rule without looking at the behavior of the integrand. If it experiences this kind of a singularity, we have to stop and think, what do we do? So in this particular example, the integral is simply not defined. It's not defined, and we cannot evaluate it. In other instances, we can think of a discontinuous function whose integral is defined. Okay, but the main conclusion from this example is that we have to look at the function and see what we can see from drawing it. And that can tell us a lot of things. Questions? Thank you very much.